Hi, my name is Poorbayan. I'm an MS graduate from the IRI Fulton Schools of Engineering, Arizona State University. And in this demonstration, I will demonstrate Dr. Samuel H. Rudy's data-driven discovery of partial differential equations, which is encoded in the form of a Python algorithm named PDE-FIND. And I'll be doing that on the nonlinear complex Ginzburg Landau equation, a model that I dealt with in my final semester, graduate semester, applied project under Dr. Jiong Kim. Now the project primarily focused on a finite difference analysis of the various unstable regimes of the Cgle, which is the complex Ginzburg Landau equation again. Before proceeding, I'd like to give a special mention to Sijie Huang, a PhD student come researcher under Dr. Jiong Kim, whose source code on simulating the incompressible Burgers equation assisted me a lot in my work. The Cgle, complex Ginzburg Landau equation, popularly it's known as the Cgle. It's a multi-scale, non-linear, unstable model, and it's also a universal model that typically describes the dynamics of oscillating spatially extended systems close to the onset of Hopf bifurcation. The governing equation of the Cgle is shown on the right. Here, A is the complex two-dimensional solution field in space X and time t, which is being solved for. Alpha and beta present in the complex valued coefficients on the RHS of the equation are measures of the linear and nonlinear dispersion effects, respectively. The simulation case I'll consider corresponds to the spatio-temporal intermittency regime. This regime is shown on the left. It is characterized by patches of stable plane wave solution, which are all those red regions in the plot, separated by regions where the solution field becomes zero, also known as holes or defects, which are those yellow staggered lines separating these red patches. The PD_FIND algorithm, which essentially will do the data-driven discovery of the governing equation of Cgle, it predicts the governing equation provided that the simulation result is available as a discretized data set, which is the solution to the PDE of interest. The algorithm basically works on these three key principles, which have been highlighted and explained in details in the three blocks. So I'll go over them one by one. I'll briefly summarize them. So essentially the first key idea, which is in the first block, is to collect the data from the input data set, which includes the solution field itself and any other additional information present, and essentially storing them in containers, typically column vectors. So once the derivatives and other combinations like the derivative and the solution field u del x, so all those candidate functions for that will represent the entire solution dynamics will be stored as column vectors. Now the second step in the second block essentially deals with building a matrix of all these column vectors, and each column vector represents a possible candidate function that represents the solution dynamics. So the matrix as a whole should represent the entire dynamics, and we will be finding out all the possible candidate functions that do so. Now the third key idea that it works on is employing a sparse regression approach for selecting a small number of active terms out of this candidate list that provides significantly large contributions to the solution dynamics. So this step also involves predicting the governing equation by assigning the appropriate weights to the selected active terms, which essentially form the RHS, right-hand side of the given equation. And it does so by a technique known as Pareto analysis. Okay, so I'll be going to my Python code, but before I do so, I ran the Python algorithm on Google Colab or Google Collaboratory. Those who are new to this notebook can easily open it from Google Drive. So if you go to the new on the left, just click it and go to more. You should get the option for Collaboratory. Then you see a notebook which is very similar to the Jupyter notebook. The interface is quite similar to the Jupyter notebook. You've got your code cells. I can add code cells for the code, and I can also add text cells to add descriptions or comments, etc. On the left, I have a section where I can upload the necessary data files and the required external packages that will be run in the Python algorithm. I highly urge you to go through Dr. Rudy, Dr. Brunton, and Dr. Kutz's work, which is again of the same name, data-driven discovery of partial differential equations. And Dr. Rudy has posted a convenient YouTube video, which sort of gives a brief idea of how his algorithm works. So definitely I urge you to go check it out. Okay, going over to my Python algorithm. So this is the Python code where I run the PD_FIND algorithm, and the simulation case I considered is the spatiotemporal intermittency regime. Alpha and beta are again measures of linear and non-linear dispersion effects respectively. U is the complex amplitude, complex solution field of interest, and this is the Cgle. So PD_FIND will try to predict the right-hand side that corresponds to this temporal term. So also the input data set is of size 1000 cross 1024. That is 1024 spatial measurements and 1001 time points. So the first thing which is done is obviously importing all the necessary packages, and of course PD_FIND, which is imported externally. Then I've also got the scipy.io imported as CO. Then the next step is to load the input data set, which contains the 2D solution field itself, 1001 cross 1024. And the space and time domains, the space domain being represented as a row vector and the time domain is represented as a column vector, and all of that are stored in separate data sets so that if the values are used again later, then at least like we don't have to deal with these nomenclatures. Then using these values, dx and dt are calculated. Then the length of the spatial and time domains and also the shape of the solution field are printed. So the shape is printed over here and the respective lengths of the two domains are printed over here. This code cell primarily deals with getting this 3D plot. So I've got my plot commands over here. Then I'm setting the Z limits, introducing ticks along X and Y, adding a color bar, and finally giving it a title and the appropriate X and the Y labels. So the last function, show under plot, what it does is it eliminates any unnecessary caption that usually appears on the top right corner of the plot window. That's unnecessary, and yeah, it's just a safe thing to use it to avoid that. So the next code cell primarily deals with implementing the first two steps rather of the PDE-FIND algorithm. So basically building a list of candidate functions that completely represents the solution dynamics. And Dr. Rudy suggested two approaches. One is using finite differences when the data available is clean and not random, but if it's random and noisy, then he suggested polynomial interpolation to evaluate the derivatives and the other nonlinear terms that again represent the solution dynamics. So for performing polynomial interpolation, I need the degree of polynomial, which is 8, and the width of the windows in X and T in which the interpolation will be performed. And I've got the respective lengths in the two domains, M and N. Then I'm simply pre-allocating empty containers to store the space and time derivatives. So I've got my U underscore T, which is del U del T. Then I've got U underscore XX, which is del to U del X2, the solution field U, and there is this nonlinear term that has an additional parameter in absolute of U, which is magnitude of the solution field. So the first for loop evaluates the time derivative on the left-hand side of the equation. And that's done by first evaluating the real part and then the imaginary part. So both of them are done separately and then combined together to get the time derivative. The second loop essentially performs the same thing to evaluate this spatial derivatives. So it starts by evaluating X underscore derivatives, and then the values are used to store like the U underscore X and U underscore XX values at each solution point. So these evaluated containers are all matrices of size n cross m, and they need to be transformed into column vectors, which will all be stacked up in these code lines. So they all get stacked up in this candidate list where, so essentially a matrix where each column vector will represent one of these candidate functions. So what I'm doing here is basically using the build underscore theta function, which is available in the PDE_FIND. And I'm using that with additional information, which is absolute of u. And I'm building this list of candidate functions, all possible candidate functions that completely represents the solution dynamics. Then I'm simply displaying a description of the candidate functions considered. The last code cell does the third job of PD_FIND, which is employing a sparse regression. In this case, the strich function train strich under PD_FIND, which uses a tolerance and an L0 penalty term to iteratively arrive at a sparse set of weights that pick out the active terms out of the candidate list evaluated in the last code cell. So this sparse regression approach will pick out those active terms which contribute significantly more to the solution dynamics than the other non-active terms. So I've got my W, which essentially represents the sparse set of weights that that we are using to pick out these active terms, and that's being finally displayed in conjunction with RHS_DES, which was already found out over here. So the RHS_DES represents the list of all possible candidate functions, and with W being combined with it will predict the governing equation of the Cgle by trying to give the best representation of the possible terms that are mainly contributing to the solution dynamics. So this is the prediction that I've got. As you can see, the algorithm does a good job, if not a great job at predicting, because I've still got some of the non-active terms. I've tried a dozen, in fact, more than a dozen combinations of tolerance and L0 penalty. There was not a clear trend as to how I should approach it, but when I was decreasing the L0 penalty term, I was getting more non-active terms. So based on that, I tried to arrive at an optimum combination. So the downfalls of this algorithm were, firstly, I didn't get the exact RHS, which is shown over here with alpha as 0.5 and beta as -1.5. And also this algorithm takes quite a lot of time. I'd also like to add that my simulation case result was of a larger size, but Dr. Rudy suggested that in all his sample cases, he considers randomly selecting equidistant points along space and time. So considering a reduced data set, otherwise the algorithm is quite time consuming. And when it comes to accuracy with which it predicts, it shows a pretty good accuracy. So I've got probably 4th order errors over here, but yeah, it's pretty accurate. And that's the end of my demonstration. Thank you.